So I'd like for this video to serve as a consolidation of examples and also concepts. So first, I'm going to cover the basic concepts as I understand them, and then we're going to look at examples, namely homework examples that basically illustrate those underlying concepts. So in order to essentially start from a point that isn't so daunting, I guess. We'll sort of start from scratch. And the basic topic here, or the overarching topic, is to find extrema. And by extrema, I essentially mean absolute extrema or local extrema. Now, if someone says extrema, and let me go ahead and change my color here. If someone says extrema, the extrema is sort of, it's an umbrella term in particular because it encapsulates a lot of things. So the basic idea here is that when someone says extrema, they could be referring to a whole host of things. They could be referring to absolute extrema, or they could be referring to local extrema. And when we're talking about absolute extrema, you can either have a absolute minimum. You could either have an absolute minimum, or you could have a absolute maximum. And the same is applied here. If you have a local extremum point, you could either have a like a local maximum, or you could have a local minimum. So when someone says extrema, they could be talking about absolute extrema or local extrema. And since they could be talking about local extrema, they could in essence be talking about a local max or a local min. So I think a good way to sort of consolidate this information is to perhaps look at a graph. So if we're looking at a graph here, that essentially is a function with maybe it looks something like this. So the basic idea here is if I were to sort of innocently ask you, what's the highest point and what's the lowest point of the graph, perhaps you'd say that this is the highest point, and if you're looking throughout the graph, perhaps you'd say, this is the lowest point, excluding the endpoints for now. Of course, there is a case to be made where we could say, these are the lowest points, but we'll sort of skip over that for now, and we'll say, this is the lowest point. And so with that sort of understanding, we could see that this point here is sort of the throughout the entire graph, or you may hear people call it throughout the entire domain of the function, this is absolutely the highest point on the graph. And this point here is absolutely the lowest point on the graph. And so that's essentially what they mean when they say absolute extrema. So both of these points are absolute extrema because one is absolutely the smallest value, not the smallest value in terms of magnitude, but it's the lowest point on the graph. And this is an absolute, this would be an absolute max because it's the highest point. It is absolutely the highest point throughout the entire graph. And then maybe we can start thinking about local extrema. And so when I say local extrema, I'm really talking about, locally, which point is the greatest, which point is the smallest. We already have sort of we already have the absolutes. We already know what's absolutely the greatest and what's absolutely the smallest. Now we're sort of looking at small neighborhoods on the graph where perhaps certain points are greater in that locality, in that neighborhood. So if we look at this point here, this point isn't the greatest point on the entire graph, but it just so happens that if you look at this small neighborhood, and this should actually be perhaps a little more curved, like something like this. And so if we're looking in that small neighborhood, then we actually notice that in this neighborhood here, this point is the greatest point. There's really no other point around it that is essentially greater than that point in terms of height. So we say that, it's this would be so this we said was an absolute maximum. And this point here we said was a absolute minimum. And for this point here, we would essentially say that this is a local maximum, because in its own neighborhood, in a small neighborhood, it is essentially the greatest value in terms of height. So it's a local max. And this guy here, it's not the smallest point throughout the entire graph, but within this small neighborhood, within this locality, it's the smallest. Because if we sort of zoom in on this, if we zoom in on this point, we'd see something like, this. And if we look in a small neighborhood or a small area in close proximity surrounding this point, there are points that around this point, but they're all smaller than this point, or they're all, this is the lowest of all the points. This point's higher than this point. This point's higher than this point. So we would call this a local minimum. So a local max and a local minimum. And so that's the idea, right? So all these points are classified as, extrema, right? Because they're at the extremes and to some extent. But Extrema has deeper classifications, right? The first classification, the first layer of classification is to say that it's an absolute extrema. The second layer of classification is to say it's a local extrema. And then we can go deeper and say whether a local extrema is a local maximum or a local minimum. And then, of course, we can go deeper with absolute extrema and say whether it's a local, or we could say whether it's an absolute minimum or an absolute maximum. So that's the basic idea. And so when we're looking at this graph, we essentially want to look for those points, which of these points are local maximums or local minimums or absolute maximums or absolute minimums, so on and so forth. So now we can sort of revisit this example and perhaps piece things together. And the first thing to notice is that let me go ahead and change my color here. The first thing to notice is that if we're looking at f of 0, like if we say f of 0, if we plug this value in, we would get here. Now, this point could be said to be a absolute, not an absolute, it could be said to be a local minimum. So we're going to say that this one is a local minimum. Now, why do I say it's a local minimum? Well, it's definitely not the absolute minimum, because there are points, all these points here are essentially lower than this point. It's not the absolute minimum. There are still other points that are, that are lower than it in a way. So this would be a local minimum. And as we move on, if we look at f of, let's not look at f of 1 for now. I'll clarify this later. Let's look at f of 2, right? So 0, 1, 2. This here would be so f of 2 would be a local minimum, in particular because, it's not the absolute lowest value throughout the graph. Again, these are still lower than this value here. So we can't really say that this is a local minimum. We can't say it's an absolute minimum. We would be forced to say it's a local minimum, right? Because if we zoomed in on this particular point, kind of like this, all these points here to the left and to the right, these are all small. These are all greater than this point. They're all higher up than this point. So this is definitely a local minimum. And so, well, a very natural question is to ask, okay, well, what about these points on this line here? So if we sort of extract this off to the side and we say, okay, this is what we're looking at, right? What about all these points? Are these local minimums or are they local maximums? sort of what's the deal here. And the basic idea is that, we want to essentially hold these points up to the same scrutiny that we were holding the other points. If we draw a point here and we look at a small neighborhood, is this a point where throughout the entire neighborhood, it is either the smallest point or the biggest point? And, looking at this type of line, quickly we can understand that, everywhere on this line, for every single point in their own neighborhood, there are points that are greater than this point, and there are points that are less than this point. So it's neither a local minimum or a local maximum. So every single point on this graph, I could draw a point here and then look in this small neighborhood. And I can see that there are points that are greater than this point, and there are points that are smaller than this point. Therefore, this point or any point on this type of graph, on a slant, can't really be a local minimum or a local maximum, right? And it definitely can't be an absolute maximum or an absolute minimum, right? That's just not possible. So that's sort of the basic idea here, and that's why we're not even looking at these points. We're really looking at these valleys, and where the graph does something a little more eventful or interesting. And so with that in mind, we're not including these points. And then we divert our attention to this point here, which is 2, 3, 4. So at f of 4, so what's happening at f of 4? Well, think about it, right? So this is throughout the entire graph, this is the highest point on the graph, and it is therefore an absolute maximum, right? Now, I can't really say that for any other point. I can't say that this point is the highest of all points, or this point, is the highest of all points. I can really only say this for f of 4, and therefore f of 4 is a absolute max. But what I want to sort of introduce is that, and maybe I'll go ahead and write this here, that the absolute, or I could say all absolute extrema are also local. So what I mean to say by that is that if I have this point here, and it is, it is essentially it is the largest point, or the highest point throughout the entire graph. It's the largest, or the highest, you can say. This is the absolute extrema. I can definitely say that it's the highest point throughout the entire graph, but I can also say that within its own locality, within its own neighborhood, it's locally still a absolute. It is locally it is a local maximum in its own neighborhood. You can think of it like this, right? If we're looking at, if we're looking at, let's say, suppose we're looking at a city, right? And in the city, there are, this is one neighborhood, this is another neighborhood, this is another neighborhood, this is another neighborhood. Suppose, Bob is really tall. So Bob is really, really tall. Everyone else is really, really small, right? So in this neighborhood, Bob is really small. I mean, all these other guys are really, really small. In this neighborhood, there are a bunch of other guys that are small. In this neighborhood, there are a bunch of guys. And in Bob's neighborhood, there are also a bunch of guys that are small. So the basic idea is that, Bob is definitely an absolute max, because throughout every single neighborhood in his city, he is the tallest guy. But that doesn't change the fact that still in his own neighborhood, he's the tallest guy. So in the same way, just because you're the largest point throughout the entire graph doesn't mean that you aren't also in your own neighborhood locally a large point. So all local, or I'm sorry, all extrema are still local extrema. So if I say that this is an absolute max, then this is also a local max. So that's essentially the idea. And so what that tells me is I can then say that I can then say that, f of 4 is an absolute max, which I said, but also within its own neighborhood, f of 4 is a local max. That's the idea. And so sort of moving on here, we see point number 5. Point number 5 is a minimum. It's a local minimum. So f of 5 is a local minimum, in particular because, there are still points that are smaller than this point. So it's not an absolute minimum, but in its own neighborhood, if I were to zoom in on this particular point, in its own neighborhood, there are points that are greater than it. There are points that are, there are points that are greater than it on both sides. So it's a local minimum. It's the smallest point around. Therefore, f of 5 is a local minimum. And then, if we look at f of 6, in this locality here, it's the greatest of the points around it, right? And so we say that f of 6 is a local max. We'll say f of 6 is a local max and f of 5 is a local min. And you may be sort of curious as to why, like I said this, right? So what we're doing is we're looking at where we said, we're looking at a neighborhood. So we're looking at this neighborhood, and the points around it are essentially either they're both less than, right? So all these points are less than this point. All these points are less than, this point. And so therefore it's a local max. And I think that basically concludes it. We definitely don't have, so a good question to ask here is, why don't we have a absolute minimum, right? And, so all these points are essentially, they're the lowest points in the graph, right? This point isn't the lowest point in the graph because it's not filled, right? It's not defined. So we never actually reach the lowest point, but we get closer and closer and closer and closer to this point. So, if we look at this point here, if we're looking at something like this, in this neighborhood for all of these points, and we can't really say this point because it's not filled, but for these points in this neighborhood, we can't say that it is either a local min or a local max because there are always points that are greater than and less than to each and every point on that line segment. So we can't really say that any point is a local min or local max, and we definitely can't say that this point is a local min or local max. And the other fact is that as we get infinitely closer to this point without ever reaching it, which is sort of stemmed off the idea of limits. So we never get to a point that is a local min or a local max. And so that's the basic idea. That's the basic idea. Sorry about that. And so that basically summarizes our answers here. We said that f of 0 was a local min, f of 2 was a local min, f of 5 was a local min, and f of 4 was an absolute max and also a local max, because all absolute extrema can also be local extrema. And we said that f of 6 was a local max and f of 1. So we said that we would skip f of 1, and now we sort of want to revisit f of 1. So at f of 1, we're essentially looking at a situation where there's like a hole, and there's a point here. So how we want to deal with this stuff is that, we want to look at the neighborhood, right? So we're looking at a neighborhood of the points around it, and we act as if though this hole was filled, but it's still on this level, right? So we're looking at this neighborhood, and from this perspective, all these points in this neighborhood are greater than this point. Therefore, this point must be a local min. It must be a local min. And it's not the absolute min, because remember, we still have these points. These points are still less than everything that we see But these aren't local min per se because we never actually reach a point. But here, this would be a local min because in its own neighborhood, it's the smallest point. And I know this may seem weird to sort of disassociate this point and then consider the points around it, even though this point isn't here. But that's essentially what you have to do. We're looking at a neighborhood and we're seeing that, from this perspective, these points, all of these points are greater than our original point. So that's essentially the basic idea. So this question here essentially wants us to draw a graph meeting the following conditions. There must be an absolute maximum at 5, an absolute minimum at 2, a local maximum at 3, and a local minimum at 2 and 4. So let's go ahead and try to draw this graph here. So if we're looking at a graph and there must be an absolute maximum at 5. So if we're looking at 5 on the graph, there must be a point that's an absolute maximum, but it can't be like this, right? Because if it were like that, then, this would in fact be a local or even an absolute minimum, right? Because all of these points, every single other point that you could draw within a small neighborhood would essentially be greater than this point. So, this would be a local minimum, right? What we really want at 5 is something like this, where all the other points are essentially less than the maximum. So at this point here, at x equals 5, we have to have something that looks like this, right? We know this for sure. We don't know how the graph connects and stuff, but we know that we have to have this shape. We have to have this shape here. So absolute max at 5, and then it says absolute minimum at 2. So we're gonna have 2 here, and apparently there's gonna be a minimum. So it can't be like this because this would imply that this is a maximum because all these points are less than this point. This would be a maximum condition, a local maximum condition. So we have to draw something like this where we have a local minimum condition because all these points are greater than this point. So it would be a local minimum condition. And so we'll say that we have something like this. And then we have a local maximum at 3. So if we're looking at 3 here, it says we have a local maximum. So, at 3, we definitely can't draw something here, right? Because it said that there was an absolute minimum at 2. So that this is an absolute minimum at 2. So if I drew this here, if I drew this here, then this point wouldn't be the smallest point on the graph. This would be. So it definitely has to be up here, right? An absolute maximum, and it definitely has to be this shape. It can't be this. It can't be, it can't be this shape. This would be a minimum condition. This would be a maximum condition. So we would want to have the maximum condition. So we would say local maximum at 3, right? And then it says local minima at 2, and then end 4. So if 4 were here, it said we would want a local minimum. So it should be a minimum condition where all the points around the actual point are smaller than this point. So this would be a minimum. This would be a minimum condition. So if you were to connect this graph, you would essentially have something like this, right? Yeah. So this would be essentially how you would connect it in. You could see that you have an absolute maximum at 5, an absolute minimum at 2, right? And then a local maximum here at 3 and a local minimum at, so when it says local minimum at 2, right, we're just leveraging the fact that, hey, this is an absolute minimum here, right? This is an absolute minimum. But remember that if it's an absolute minimum, then it must also be a local minimum. Within its own locality, it is still the lowest point, or the lowest point. And throughout the entire graph, it is the lowest point. So we say that it's the absolute minimum and the local minimum. And that's how our graph would look for this particular question. So this is the next question here. And essentially what we're given is the graph of sine of x. So if we're looking at the graph of sine of x, we essentially start from the origin, and actually let me go ahead and have something like this. We start from 0, 0, and then we essentially move like this in this fashion. And the sinusoidal wave for sine of x is actually derived from it's actually derived from the unit circle. So this is 0. You can think of this point as being 0, and then this point is pi over 2, right? So half of the circle, so this is 1/2 of the circle, right? And this is the other half of the circle. So at the halfway point, we are at basically half. This is half of the circle, and then you took half of that. So this is the circle, and then I took half of that circle. I would essentially have pi over 2, right? And then I would have pi, because that's the halfway point. And then here I would have pi, and then here I would have 3 pi over 2, right? Because that's the other half of the second part of the circle. And then I would have 2 pi, which sort of concludes it at this point. So with that in mind, this is sort of a messy drawing, but we can sort of draw it again and say that these are essentially the points that we had for sine. We had pi over 2 here, we had 0 over here, and then we had pi over here, and then we had over here we had 3 pi over 2, and then over here we had 2 pi. And so that's the graph for sine of x. But this guy here, if now we're looking at an interval, right? So it's saying that, hey, look at the graph for sine of x, but only choose an interval to answer this question. So it wants us to say, okay, choose this interval to this interval, and only look at this graph, this part of the graph, or choose this part to this part, and only look at this part to determine what your extrema is. And so it's actually given us, where to look. And so when it says 0 is less than x is less than or equal to pi over 2, this is sort of a fancy notation for something that I think a lot more people are familiar with when they say, 0 to pi over 2. This is where you should look. So it's saying, go from, look at 0. And I don't think this is the right question. Yeah, so this is number 20. It's actually not on the homework. We're actually supposed to look at 19, but still, if we're looking at 20, I guess it's fine. I think it'll still demonstrate what we want to essentially convey. But I think that even for 20, we're looking at, even for number 20, we're looking at sine, except the interval. The interval is changed. So for 20, or for 19 rather, we're looking at sine of x, but the interval is 0, including 0, and then 2 pi over 2. So what we should have here is 0, and then that's essentially the interval that we're looking at. And I'll explain sort of what that interval really means, but we're looking at 19, and it's kind of like that, yeah. So if it says a is x is, x is, this is basically a fancy way of saying that x is between a and b, right? Because if you have x is less than a, which means a must be here, right? X is x is greater than a, so x must be here relative to a, and then but x is still less than b, so b must be here. So x is less than b, we know that, right? Because it's behind b. And then x is greater than a, we know that because it's in front of a. And so it's just trying to sort of tell you that, hey, this is what we're saying, that this is what we're saying. X should be somewhere in between A and B. And so this is basically a translation of our interval. And so basically this means A, B, because it's not including A or B. And what I'll talk about what it means by when it says including or when it wants us to include, but the basic idea is that these can be translated to notation that we're familiar with. So if we say that A is less than, or for all x that are between A and B, but we include A and B, then we're talking about something like that. We're saying that we're including A and B, so we've changed these signs to greater than and less than, but we've added A equal to. So if I said -1, 2, or if I said x, well, that would just mean that I'm taking -2 and I'm including it, but the 3 I'm not including, so it's just open. So if I said if I had a graph like like this, and I had 3 here and 8 here, and I said that I have an x value here, so x should be greater than 3, obviously, right? But it should also be less than 8 in order for x to be between 8 and 3. And this interval would look like this, 3 and 8, right? So if I took a portion of this graph, I would only be looking at this. So I'd be looking at this, right? And I'm not, this is an open hole here, open hole. I'm not actually including the endpoints. If I want to include the endpoints, I'll add this equal to sign, and suddenly these endpoints will sort of close off, and now I am including the endpoints. So this notation of saying that x is less than x is greater than A but less than B is just the same thing as saying that x is between these two values. And at the same time, if I want to sort of grab a portion of the graph and say that what portion should I consider, if I don't have these equal to signs here, then I'm looking at something like this, A, B, right? But if I add these signs, then I'm actually considering something like this, where I have the holes are essentially filled. So when it says x should be greater than 0 but less than pi over 2, so pi over 2 is here, right? I have this guy and this guy, right? So I'm looking at 0 here, and I have this guy and I have this guy, right, which is at pi over 2. This is the only section of the graph that I'm looking at. So through this entire graph, I'm only looking at this section of the graph, and these are open holes. But remember, one of them is including 0. It says greater than, so I'm going to include 0 as well. So this is what I'm now looking at. And now I'm asking myself the original question, which is, where the absolute minimum or maximum, where the local minimum or maximum, so on and so forth. And in this particular case, there is no absolute max, right? Because if I zoom in on to this point, I can keep getting closer and closer and closer to this main point here and actually never reach this point. And we know that every single point along this line will have a point that is greater than or less than the point in question. And so it's never, no point on this line as we get really close to this bigger point that doesn't even exist. No point will be a absolute minimum or absolute maximum or a local minimum or a local maximum. It's just not possible. So, so that basically rules out the whole idea of there being a local min or a local max, or an absolute min or an absolute max here at this point. But then we look at this point, which is actually defined, and at this point there is an absolute minimum value at 0, 0, in particular because this point is it's the lowest point throughout the entire graph. Therefore, it's the absolute minimum, right? But we know that in its own locality, it is also the local minimum. So at x equals 0 or at 0, 0, it is both the absolute minimum and the local minimum. And so that's the idea behind this question. Just as sort of like a brief example, if I said, take the graph of x squared, right? Or, maybe something like this. We know that there must be an absolute minimum at this point, in particular because this is the lowest point of the graph throughout the entire graph. Both these points go up to infinity and they keep going up. So that means there can actually not be an absolute maximum, right? There can't be an absolute maximum because these points just keep going up and up and up towards infinity. There can't be an absolute maximum, but also at the same time, there can't be a local minimum, right? Because all these points, if I look in this neighborhood, there are points that are greater than it, there are points that are less than it. So it's not a local min or a local max. So the only thing is, on this graph at least, there is a absolute minimum at 0, 0. But so this is, let's say, -1, or right? This is, let's say, 3. What if I gave you the interval for this graph and I said, well, what would this interval translate to? And the answer here is that, we have -1 and we have 3. So we're sectioning off this part of the graph from -1 to 3. And we're going to look at it now. So now we're just looking at this part of the graph. And we know that there is a absolute minimum at this point. But now we're looking at these points, and we see that that -1 is included. So we're going to fill in that point, -1, right? But 3 is not included, so we're going to leave that as is. So this is a filled in point, which means this here is a absolute max. And it's an absolute max in particular because throughout the entire graph, it is the highest point on the graph. This is not the highest point. It's not even equal to this point because the point doesn't even exist. So this is your absolute minimum. This is your absolute maximum. And as an extension to this point, since all absolute maximums are also local maximums in their own neighborhood, we can say that this point is both an absolute max and a local max. This point is an absolute max, absolute minimum, and a local minimum. Because within its own locality, it is still a local minimum, but throughout the entire graph, it's also an absolute minimum. So that's the idea behind sort of, dissecting graphs and taking portions and then looking at them and sort of translating intervals into, something that we're more familiar with. So this question in particular wants us to find something called the critical numbers. So I guess it would help to talk a little bit about like what critical numbers are. So by definition, I guess I'll write it here on the board. If at x equals c, the derivative, which would just be f prime of c, the derivative equals 0 or f prime of c does not exist, then c, x equals c is a critical number, right? So basically, if we're looking at a graph and we have like, a c value here at, this is our x-axis, and this is one of this x values, which we'll call c, and we're looking at this, and So we can call this n and we can call this d. So, this point here, the derivative is 0. So that means it's a critical number. This point here, the derivative is 0. That means it's a critical number. At this point here, the derivative does not exist. It's still a critical number because the definition of a critical number says that if at x equals c, the derivative f prime is 0, or the derivative at that c does not exist, then it's still a critical number. So this is a critical number, this is a critical number, this is a critical number. Now, the whole idea is that not all critical numbers are essentially absolute maximum or minimum values, right? So what I'm basically trying to say is that just because it's a critical number does not mean it's a local, I guess we'll say local maximum or minimum value, right? This is basically the takeaway. What we could say is that, hey, if it's an absolute maximum or minimum, then I mean, if we find all the critical numbers, then those are also our absolute maximum or minimum values. That's not true. That's not true, because if we look at a graph like this, right, or maybe right. So you could say that, so basically what's happening is that at this point, the derivative is 0 for a second. So at this point, f prime of c is 0, right, if c was here. But then it starts being positive, and then before that it was all negative. So the idea is that this point is not a absolute maximum, or sorry, it is not a local maximum or a local minimum. It's not also an absolute maximum or an absolute minimum, because if we look in this neighborhood here, right, there are points that are greater than this point here, and there are points that are less than this point, right, on the other side where stuff starts decreasing. So this is neither an absolute maximum or a local, it is neither a local minimum or a local maximum, and yet it is a critical number. So just because it's a critical number does not mean it's a local maximum or a minimum. And that could be an interesting true false, right? You could say that, just because it's a critical number, does this mean that it's a local maximum or a local minimum? And the answer is no. So, we could have basically a graph that, if this graph was doing, something like this, the derivative was there, the derivative was 0 for, basically what I'm trying to say is, if we had something like this, right, the derivative was 0 for a second, and so the derivative here is in fact 0, so this point is a critical number. But note that just because it's a critical number does not mean that it's an absolute maximum or minimum. This is neither, or it's not a local minimum or maximum. This is neither. So the goal is to first find all the critical numbers and then find the local minimum and local maximum, right? So so basically what we want to be able to do is we want to take all the critical numbers, even if they're not a maximum or minimum locally, and we'll funnel those. We'll look through each of them and then pick and choose which are absolute local minimums and local maximums. So when we're given this, when we're given this function, we want to find the critical numbers first, and then we'll funnel that down and simplify that down to, which of them are absolute max and absolute min, or local min and local, sorry, not absolute, but local minimums or local maximums. So we're only looking at, well, actually, I believe that we are, for this question in particular, it says find the critical number. So it's not really wanting us to, take this as far as finding out which are which. We're just supposed to find all the critical numbers. Now, some of these critical numbers may not be maxes or mins, but for this question, it's really not that relevant. So what we do to find all the critical numbers is we look back and we say, okay, where is the derivative equal to 0? So first we take the derivative of the function, which is 12x squared cubed plus 24x squared minus 96. And once we've taken 96x, once we've taken the derivative, we set the derivative equal to 0. So we set this 12x cubed plus 24x squared minus 96x, and we set that equal to 0, and then we solve. And then wherever those x values, whatever those x values reap, we essentially have a critical number at that point. So in this particular case here, what we could do is we could factor out a 12x, and because 12 is common, x is common. And then what we have is we have an x to the first, or x squared plus 2x, right? Minus 8 equals 0. And then this is a manifestation of the zero product property, which says that if you have two things multiplied together, one of them must be 0. So we set each of them equal to 0 individually, and then we solve. So we say x squared plus 2x minus 8 equals 0. So we solve for this one, and we get x equals 0. And then we also want to solve for this one, right? So we're looking at -8. We're looking for two numbers that that multiply to -8 and add to -2. And 4 and 2 comes to mind. And in order for this to be positive, we would have to have this. And in order for this to be negative, we would have to have this. So this multiplies to -8, and it also adds to +2. So we would just say that this is x plus 4, and then x minus 2 equals to 0. And again, this is another manifestation of the zero product property, where if you have two things multiplied together, then one of them must be 0. So we'll say that x equals 0 is still our critical number in this case, but now we're setting x plus 4 equal to 0 and x minus 2 equal to 0. And this is x equals -4 and x equals +2. So these are essentially our critical numbers. So these are the numbers at which the function is doing something that can potentially be a maximum or minimum locally, but not necessarily, if that makes sense. And so I think as we move on, we'll see that we'll develop ways of actually narrowing this down from, getting all the candidates. We have a bunch of, it's kind of like a lineup, it's kind of like a lineup, where, you're sort of looking at a bunch of people, and you're asking, hey, in one of those movies where you have a bunch of criminals sort of lined up, and you're like, hey, you're a critical number, you're a critical number. All of these are candidates. You're a critical number, but which one is the local min or local max? This one, right? Or whatever. So it's like you're filtering through to find out which one is actually, the local min max, if that makes sense. So you're just filtering through. And this part just got us down to only finding the candidates and not actually finding which ones are the local mins or the local maxes. So this particular question here is asking us to find the absolute extrema on a closed interval. So this is basically derived from something called the extreme value theorem, which basically says that if you have a graph, and you have a closed interval on A and B, which means a continuous closed interval. So these they're closed points, so they must be black dots, right? They must be filled in holes. And if it's continuous on this interval A and B, then there must be an absolute min and an absolute max, or an absolute min in this case, absolute max. So if basically it's continuous on the closed interval, then it guarantees absolute min and absolute max, right? It doesn't say anything about local min or local max. It just guarantees that there is an absolute min and an absolute max. So basically, because this would be the absolute maximum, this would be the absolute minimum, it guarantees it. So this is trying to say, hey, if I give you any continuous closed interval, then you must be able to find, first find the critical points, and then funnel those critical points down to which ones are. So basically, this is telling us to use the closed interval method implicitly. And the closed interval method essentially says, find the critical points. And then once we find the critical points, we essentially want to take the critical points, plug them back into the original function, take the endpoints, plug them back into the original function, and whichever basically, after we get a bunch of values gathered up after having plugged everything into the function, whichever is the smallest value is the absolute minimum, whichever is the biggest value is the absolute maximum. And this makes sense, right? Because if this function was maybe something like this, right? It's something like this. So, or you could maybe say something like this. So, what we're doing is we're first asking ourselves, where are the critical numbers, right? Where are the critical numbers? And, once we find all the candidates for where the critical numbers are, we can then plug those critical numbers back into the function to see which one is the highest. Does that make sense? So once we find out which one is the highest, we essentially say, okay, this is the highest, so this is the maximum, this is the absolute maximum, or this is the lowest, so this is the local, so this is the absolute minimum. But then, so it should be enough to just find the critical numbers, plug them into the function, and then say, hey, this is the highest, so this is the absolute max, this is the lowest, so this is the absolute min. But it's actually not enough, because think about cases where, we could have our extrema, the lowest point on the graph, the lowest point on the graph is at an endpoint, and the highest point on the graph is at an endpoint. So we also want to take the endpoints and plug them into the function in order to check, hey, maybe the endpoints could be the absolute max or the absolute min. In this graph, they weren't, right? In this graph, this was the absolute max, this was the absolute min, but there are still other graphs where perhaps the absolute max or absolute min are on the ends. And so that's why we essentially want to take this particular function, find the critical numbers, take the critical numbers, plug them in, but then also plug in the endpoints to make sure that they aren't, culprits. So first, let's take the derivative. So f prime of x is equal to 6x squared minus 6x minus 12. And then we want to set this equal to 0. So 6x squared minus 6x minus 12 equals to 0. And then we can factor out a 6. So we can say 6x squared minus x minus 2 equals to 0. So 6 should equal, so now we're setting each of these to 0 to find out, zero product property again, right? This is not possible, so we eliminate that. So now we just have x squared minus x minus 2 equal to 0. We're looking for two numbers that multiply to -2 and add to 1. 2 and 1 comes to mind. In order to make this possible, there must be a negative here and a positive here, because these two numbers multiply to -2 and they add to -1. So this would be x minus 2 and then x plus 1 equals to 0. And then x equals to 2, x equals to -1. So these are essentially our critical numbers, x equals 2 and x equals -1. So what we essentially want to do at this point is we want to take 2, plug it back into the function. We'll take -1, plug it back into the function. And then we'll take -2, plug it back into the function. Then we'll take +3 and plug it back into the function. And then whichever reaps the smallest value is the the absolute min. Whichever reaps the greatest value is the absolute max.